It's a new chapter. Chapter 5 is about integration. So before we get into the first section, I want to just give you an idea of what the point of this chapter is, and then that will help make sense of where we begin because we kind of had this goal in mind, and so it helps us to just realize the beginnings, and we're going to be working toward that goal. So you see my drawing here, a very similar drawing to one that I had in the math. At the beginning of the semester, I presented a few slides on what is calculus, what is Math 121. So half of the course is about derivatives, differentiation. That's the first branch of calculus. The second branch of calculus is integration. And I don't know if you remember from then, probably not. It turns out that the two ideas are actually they're very different concepts, but the way we end up going about it, we end up doing the opposite of the way we find derivatives to do integration, or integrals is what we call them. Okay, so here's the idea, and here's the goal. Imagine a function, any random function going across, and then I'm going to mark a and b here on the x-axis, and I draw these vertical lines up to meet the function, and I filled in this area. So the goal of this chapter is to be able to find areas like that. What is the area between f of x and the x-axis, starting at x equals a to x equals b? From the x-axis up to the function, can we get that exact area of this curved region? Turns out the applications to that are endless. It doesn't seem like it would be a big deal, okay, these weirdly shaped areas, but it goes way beyond just areas, the things that we can apply this to. All right, even more than derivatives in its applications. So we're going to call the answer to that the definite integral. Um, we would say the definite integral of f of x from x equals a to x equals b is, and we would be specifying the exact area there, geometrically anyway. It's going to take a little work to build up to the definite integral. I don't think we actually see it until 5.3, 5.4, and we really don't even develop a good technique until like 5.5. And that's kind of the culmination of the chapter. Okay, so where do we begin in 5.1? So I mentioned that doing integrals, it turns out, is the opposite process as finding derivatives. So we begin with antiderivatives, and then what we're going to call the indefinite integral. Okay, so the area is a definite integral. We're going to look at indefinite integrals for now. All right. And antiderivatives are the opposite of derivatives. Sometimes students like to be cute and they say, I'm anti-derivatives, but that's not what we mean here. All right, let's just take a look at an example, okay, and I'll ask this question. So I'm going to give you a derivative. I'm going to say f prime of x equals, let's keep it simple, 3x squared. Then the question will be, what is the original function? What was the original function f of x? So are we familiar enough with derivatives that we could even work backwards? Well, maybe this one isn't so bad. 3x squared, what would have the original function have been to give this as its derivative? I say, okay, well, I know that's x to the third, right? Okay. Well, that's true. The derivative of x to the third is 3x squared. But wait a second. Couldn't you have said f of x equals x to the third plus 1? The derivative here is also 3x squared because the 1 would go to 0. Oh boy, couldn't you have said f of x equaled x to the third minus 26? We could add or subtract any number we want off the end because that part's going to go to 0. The x to the third part goes to the 3x squared. So we realize, oh boy, there are infinitely many functions whose derivative is 3x squared. They're all going to begin with x to the third, but you could add or subtract any number off the end that you like. So here's what we're going to do in general. We're going to say f of x is x to the third plus c. So we're going to leave that number unknown. C stands for constant. And more specifically, we call it an arbitrary constant. It is arbitrary, meaning like it is a constant. It is one number, but it could be any one number, and it doesn't matter which. So the arbitrary, hence the word arbitrary constant. Okay. Now that we know about antiderivatives, I'm going to define the indefinite integral. I'm going to show you the notation first. Okay. I should probably say the indefinite integral notation, maybe off the end there. And we'll use the same example with the 3x squared. Now, a couple things. So the notation for integrals, kind of bizarre. It's going to make more sense as we go through the sections. There's this curved line here to start things off. Yeah, really unusual, this curved line at the beginning. Then we put the function, really the derivative, right, that we're going to work backwards from. And then we put a dx. So let me just give you an idea where these things come from. It's not going to be the full explanation, of course. That'll come later. That curved line at the beginning, it literally is a stretched out capital S. So it's like it kind of does that sort of shape, a capital S. Okay. It's capital S for a reason. We'll see that later. So we got this stretched out S, then the derivative, right, that we're looking at, and then what's up with the dx? So that's called the differential of x, and that's where the d comes from, differential, which sounds a lot like derivative, differentiate. Right? It's the same dx that you see in this notation for the derivative, dy over dx. That notation, that literally is the differential of y divided by the differential of x. Okay, so that denominator is the same thing that's appearing here. Very weird. I get it. Hopefully it'll make more sense in future sections as we see that that concept played out and we develop this idea more. These work as bookends. So we put that stretched s at the beginning, we put the dx at the end, we put the thing we are questioning there in the middle. Okay. This notation is telling us to perform an antiderivative on that. Okay. So here's what we would say. Look at the function there in the middle, or the derivative, work backwards. Don't forget to add c. So whatever you're looking at, this notation with the stretched s and the dx is telling you to find that antiderivative, x to the third, and then put the plus c, the arbitrary constant, on the end, since you might add or subtract any number there. Okay, and we call this whole thing here an indefinite integral. When we have definite integrals later, we're going to use the same notation. There'll be a little adjustment to it, but we're basically going to use the same notation. Okay, so at this point, we're just going to practice finding indefinite integrals of lots of different kinds of functions. We've already seen one. Here we go. Find the indefinite integral. Let's start with this one. Part A. So you would read this as the indefinite integral of 14x dx. It's like that symbol right there, the indefinite integral of 14x dx. What does that mean? It means we need to focus on the 14x. We need to find the antiderivative, so I'm going to put an equal sign here. We need to find the antiderivative, and then don't forget the plus c on the end. Well, let's think. what do we take the derivative of to, where do we begin so that when we take the derivative, we get 14x? You might think, oh, wouldn't that have been 7x squared? So if we take the derivative, right, the 2 multiplies down, the power drops to a first power, and then we've got the plus c. There it is. There's our answer. Okay, that's it. We did it. We found that indefinite integral. Let me just erase this, get it out of here. All right, let's try another one. They're going to get harder as we go. How about this? X raised to the 8th. Okay, so we would read that as the indefinite integral of x to the 8th dx. But our focus is just right there. What is the antiderivative of x to the 8th? Think, oh, okay, this one's a bit more challenging. Think of it this way. What was the power of x before we took the derivative? If it's an 8th power now, wasn't it a 9th power before we took the derivative? Because it had to drop by 1. Okay. When you take a derivative, that 9 multiplies down, and then you get your answer. But I don't see a number here. So that 9 must have multiplied by something, and it canceled out, and it's just a 1 now. It must have multiplied by 1/9. So the 9 times 1/9 cancels out, and all that's left is x to the 8th. Don't forget plus c. There's our answer right there. Okay. I encourage you, always check by differentiating. Take the derivative. Do you really get back to this as your answer in your derivative? Okay. All right. How about getting harder now? How about a negative exponent? Oh boy. But maybe we can use the same sort of thinking here. Don't worry about the coefficient yet. Do that later. Think about the power of x. If it's x to the negative 4, then before we took the derivative, what was the power of x? Well, we always add 1, right? It's always 1 bigger. So if you add 1, would have been negative 3. Following that same pattern. Then the negative 3 must have multiplied by something and canceled out. Must have been negative 1/3. And of course, plus c. There's your answer. So thinking about the derivative, the negative 3 multiplies down, cancels. This power drops by 1, negative 4. Of course, the c goes to 0 for any constant. Ooh, okay. If you're with me so far, you're doing well. We're building up slow. Let's get a little bit harder. How about fractional exponents? Now we're really talking. All right, and we've got 2 parts now. Well, if we're adding, then we can do the antiderivatives one at a time, right? Do this one first, then add that one. Okay, oh man, this one, 2x to the 1/3. Oh my goodness. Don't worry about the coefficient yet, just focus on the power of x. If this is x to the 1/3, what was the power of x before the derivative? So remember, we always add 1 to go back. Well, 1/3 plus 1 is 4/3. 1 larger. But then when we multiplied by that 4/3, somehow we ended up with 2. Here's what you can do. For now, think of it as 2 over 4/3. So when that 4/3 multiplies, it cancels, and you're just left with the 2. We will simplify this for our final answer, but I think this works well as a first step. Okay, plus, do this one. Oh man, x to the 5 halves. Skip the coefficient, let's just get the power of x. So we need to add 1. So we'll add 2 over 2. It must have been 7 over 2. Right? So then it's subtracted by 1. Well, then what was here? It multiplied and it canceled out. There is no number there. You could think of this as 1 over 7 over 2. So it will cancel. And of course, we need the plus c. Let's simplify now these fractions, and we will have it. If you forget how fractions work here, 2 over 4/3, think of it as 2 over 1 over 4 over 3. And you can flip and multiply. 2 over 1 times 3/4. Actually, we get some nice reducing here, and it's just 3 over 2. So this is 3 over 2, x to the 4/3. Let's think about that. If I multiply by 4/3, then the 3's cancel, and I've got 4 over 2, which is the 2. Okay. I could do the same idea here. Actually, the 1 over ends up just flipping it, and it becomes 2/7. And I wouldn't be surprised if some people even got that from the beginning. When you multiply 7 halves and you want it to cancel, well, the 2/7 would cancel everything, the 2 and the 7. So there we go. There's our indefinite integral of this one. Okay. How about something, this one's a little bit different. Get those notes off the screen. 10 over x. Interesting. 10 over x. Now sometimes students think a while about this. Think of it as 10 times 1 over x. So the 10 is like a constant multiple. It would have just carried along. What do you take the derivative of to get 1 over x? Well, of course, that's natural log x. And we need the plus c. So there, derivative 1 over x, and then it would multiply by the 10. The c, of course, would go to 0. Got it. One thing we need to mention here about antiderivatives when your result is natural log. So it turns out we need to put absolute values on this x here. And that's not obvious at all. Let me just really briefly explain why we need absolute values there. It turns out the domain, it's a domain issue. The domain of natural log x is only the positive numbers, 0 to infinity. But the domain of 1 over x is all real numbers except 0. Okay. So we can allow any value of x there. Negatives are fine. So then if we were to plug that same value of x here, well, we can't allow negatives. We can take the absolute value of that number, and then that's okay. It turns it positive. That's not a complete explanation, but I think that probably satisfies most people. Only positive numbers are allowed here. Negative numbers are okay. So we got to force that to be positive. I got one more before we will end this video. How about 4e to the x? All right. The indefinite integral of 4e to the x dx. What's the antiderivative of 4e to the x? Well, the 4 is a constant multiple, And if my derivative is e to the x, then the original must have been e to the x as well, plus c. There's my answer here. Okay. I do have a couple more examples in this section. We'll do those in the next video.